This is section 9.2, Series and Convergence. We've been talking about sequences, which is a listing of outputs when the input is a positive integer, like the first term is, here is, I've written as 2, so a sub 1 is the way we denote that, is 2, a sub 2 is 4, a sub 3 is 8, fourth term is 16, etc. And of course that's what we call a sequence. Now, today's lesson is talking about something called a series, and what a series is the sum of all the terms of your sequence. So if we use the sequence above, this is the series related to that sequence. And that's what we call a series. Now, because this is an infinite sequence up here, we could more appropriately perhaps use this adjective and say it's an infinite sequence, and that means that this is an infinite series. We're going to assume that we have infinite series for the majority of this unit. So if it's not an infinite series, you'll know because it'll clearly state that it's not the entire series. And so what we use to indicate a series, a sum of things, is, well, I kind of wish I hadn't written that where I did. But if we, after this comma, I'm going to go over to the other side, had dot, 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 so this isn't really part of that sequence. Oops. Then, oops, I'm sorry. Let me take away those dot, dot, dots because we already had the dot, dot, dots. So again, this is not part of it, part of the sequence. So what would the general term here be? Have you figured it out? If n is 1, 2, 3, 4, 5, what would you do to n to get those outputs? And I think we've seen something like this, perhaps as a denominator of a sequence earlier. I think we did. This is 2 to the nth, comma, dot, dot, dot. Make this look a little bit bigger. So likewise, kind of pull this out. I'll pretend like I'm continuing, plus 2 to the nth plus dot, dot, dot. And there's sigma notation that you learned about in pre-cal and hopefully used enough in Calculus 1, and we reviewed it a little bit, so that you understand that this is an infinite series from n equals the first term and never stopping, so going to positive infinity, and just increases without bound forever. And the formula that produces all of those numbers, of course, is our general term formula for the sequence, which is the same as the general term of the series, and that's what goes behind sigma when you want to write the sigma notation. So you may see now why it's important that we come up with that general term notation 2 to the nth, so that we can write it using sigma notation. Just like those are terms of a sequence, these are terms of a series. There are going to be times when, for some reason, it's going to end up being to our benefit to use whole numbers instead of positive integers. And so a formula for a series very well could start with n equal to 0, or actually technically any number you want. So let's say if we had like 3 plus n, 3 plus 0, we'd start with 3, plus 3 plus 1 is 4, then go to 2. 3 plus 2 is 5, etc. Okay. So, but a series sigma notation does not have to start with n equals 1. It can start with other numbers. A 0 is the other biggie that you'll see, because sometimes it's nice to start with 0 instead of 1. Now, a lot of times as a shortcut, once we've established whether we're starting at 0 or 1 or whatever, for the series, a lot of times what we'll do is we'll shorthand that notation some and just write sigma of whatever. And we'll assume that it starts at whatever we've established in that problem already, or we'll have to then assume probably the n starts with 1, which is generally what we will do. But most of the time you can take it from the context as to what the initial index value would be. So the next thing I want to talk about is something called a partial sum of a series. A partial sum is when you stop adding up at a particular place and report what you have for the sum of that part of the series. So let's find for the series that I have written above, because it works just as well as any other. It's just an example. The sum of the first one term, which is a weird English thing to say, but it's basically just whatever the first term is, because you're not really doing a sum. You're not adding anything. So the first partial sum is the first term. The second partial sum is the sum of the first two terms. The third partial sum is the sum of the first three terms, etc. I'll do one more. And what we can do with that, with those partial sums, is form a sequence, which I'll do in a second. Let me go back and do the arithmetic. Okay, so the sequence of partial sums of that series that we've been messing with this whole time, the sequence of partial sums would be 2, 6, 14, 30, 62, I think is the next one, etc. And we could have continued this until we got to what we will call the nth partial sum, which is the sum of the first n terms of that series. So plus ... plus the nth term, which is 2 to the nth, and stop. And so this sequence of partial sums would eventually get to s of n and then continue on. The nth partial sum of that series is labeled capital S subscript n. Now, an interesting thing about this is if the sequence of partial sums, if this sequence converges, the sequence of partial sums, if that sequence converges, then the series converges. So that's going to be the test for whether a series converges or not is that we have to find the sequence of partial sums and then find out if it's going to converge or not. Okay. So since that's a sequence, we can use the test that we learned in the prior section to test for the convergence of that sequence. In other words, if the limit as n approaches infinity of s sub n is a real number, not infinity or negative infinity, but an actual real number, then that would imply convergence. If you get infinity or negative infinity, it will diverge. And then there were other examples like the alternating, oscillating sequences, which would be oscillating series, perhaps. If that's the kind of sequence we get as an alternating one, then it will diverge. And if it, so anyway, those are some of the things that can happen. So we'll be going back to section 9.1 to test the series for convergence, because the sequence of partial sums is what we look at to make that determination. All right, so look at the definition of convergent and divergent series. It's basically what we've been talking about. So if the sequence of partial sums, the sequence built on capital S sub n, if it converges to S, they used S and I probably should have too. So let me fix that so that that's in line with what they say, because that's actually better. Sorry, it did take me a second to realign things. If that equals a number S, that's a real number, then the series converges, and it converges to S. Okay. If that sequence of partial sums diverges, then of course the series diverges as well. So let's look at this series. 1/3 plus 1/9 plus 1/27 plus 1/81 plus ... And have you figured out what the general term for this one will be? You might have noticed that those are all powers of 3. And so 1/3 to the n, like when we put in 1, we'll get 3. Put in 2, we'll get 9. That's actually correct. Those are the right powers of 9, starting with the right one, I mean. So that's our general term. So let's find the sequence of partial sums. So the first term is S sub 1. A sub 1 and S sub 1 are always the same. S sub 2 is the sum of the first two terms. S sub 3 is the sum of the first three terms. Move this down a little bit. There we go. S sub 4, sum of the first four terms. This next one, I'm not going to write all of it out. So do all of that plus 1/243 be the next one. And that's 121/243. And the question is, can we come up with a formula for S sub n? Oops, wrote 5. Didn't mean to do that. For S sub n. That's the question. So if we write that sequence of partial sums, 1/3, 4/9, 13/27. 40/81. 121/143, etc. What do you think this is converging to? Just before we actually get to how we'll find that number. In a minute, we'll talk about how to find it without having to resort to this thought process. But I just kind of want to have a sense of, do you know what this is, if it converges, what it converges to? So, I'm going to write down a few of the decimal forms of these fractions so that we can use that to help us make a decision. Maybe you can see it in fraction form. Maybe you can't. Let's see, this one, 0.497. Oops, 4. Well, rats. 4, 9, 7, 9, 4, 2. And as it turns out, if we had found S sub 6, it would have been about 0.499314. And so, do you have a guess of what this, well, first of all, do you think it's converging? Do you think that those answers are headed towards a value? So, in other words, what do you think it converges is the first question, and if so, to what? And we haven't found a formula for S sub n, but if it does converge, then that means we're going to be finding this limit. And what do you think it is? Well, to me, it looks like it might be converging on 1/2. This is a guess at this stage. I'm just using numbers to kind of inform me what's going on. Anything I come up with is truly a guess. I may be very confident in my guess and think, I'm pretty sure I know what that is. But on the other hand, I might not. So, in fact, I can be maybe misled. Maybe it's really headed towards 0.499999997 or whatever. So we just don't know. But I think 1/2 is a good guess. So my question is, can we find a formula for this sequence of partial sums? Well, the denominator, I think, is clear. I think that's easy because we've seen that already. That's powers of 3. So that's 3 to the n. So for 1, that would be 3 to the first. For 2, that would be 3 squared, which is 9, etc. So that tests out. So can you see how the numerator would be formed? Well, what you might see, let me kind of point this out, something to look for, is if you already know how to get the denominator, is there any way you could play with that answer to get the numerator? Because what I'm seeing is, no, I'm not. Sorry, I'm not seeing anything. Well, maybe I am. It looks like, if you take half of the denominator, 1/2 times 3 to the n, what could I do to that to get the whole numerator correct? Well, let's do like 27. Half of 27 is 13.5. What could I do to 13.5 to get 13? Well, I'm going to write minus a half, or minus 0.5, as a guess. Maybe I'm right. So let's check it out before we commit to that. Half of 81 would be 40.5. Take away a half. Hey, it was working. Yep, I think that's it. And if we were to factor that, the 1/2 could come out front of the rest of the numerator. Like that. And in fact, we could simplify it further, although it will start not to look exactly what we were thinking to begin with. But we could say that that's 3 to the n minus 1 all over 2 times 3 to the n. And of course, that 2 will end up canceling with something in the numerator each time. So, what is the limit as n approaches infinity for 3 to the n minus 1 over 2 times 3 to the nth? Well, let's pretend like we have absolutely no clue how to do this limit for just a minute. And we're going to come back to this in a minute and see if we can find a way to do this. The thing is, I was actually able to kind of figure out this one. I don't know if you followed all of my thinking process and my reasoning, but I was lucky that I actually saw something that created those numerators, and it just happened to work. I'm afraid to say that there are going to be plenty where you just can't look at it, so you won't be able to come up with S sub n like we did here. We actually came up with it. And so we're going to be kind of flying blind with this approach because sometimes we just will not be able to come up with that formula for S sub n. So we'll come back to this one later and see. So let's do one. Well, we'll come back and confirm this one. I'm going to go ahead and do this limit, I think. Because I think now that we have it, we might as well. So if I substitute in infinity, I'm going to get infinity over infinity, which means I've got to go to a function of x instead, because I want to use L'Hopital's rule. You cannot take the derivative of a sequence, but you can of the related function. So there we go. And because we've got infinity over infinity, we can use L'Hopital's rule. The derivative of 3 to the x is 3 to the x times natural log of 3. The derivative of 2 times something is 2 times the derivative of that something. And the derivative of 3 to the x, again, is 3 to the x times ln of 3. Then if you simplify algebraically what you just came up with, that simplifies to be 1 over 2, and the limit of a constant is that constant. So actually, as it turns out, our guess was good, and the sum of that series is 1/2. I want you to think about what I just said. The sum of that series is 1/2. So if you go back to that infinite series up here, if you add all of those numbers and never ever stop, the actual sum of that entire infinite thing is 1/2. Now, when you first hear something like that in Calculus 1, where you're adding up infinitely many things to get exactly a particular value, that seems a little bit odd, but we've been doing that now in this course several times for a while even. When we find the area under a curve using a limit of, as n approaches infinity, of a sigma expression for the area of the rectangles that approximate that curve, then that gives us the exact area. And of course we used an integral for that. That's not what we're going to do here, but it's something that we've encountered before, the concept of infinitely many things add up to be a nice, pretty constant like that. Okay, so let's look at our next example. This is a series, n equals 1 to infinity, of 1 over 2 to the nth. So it's going to look a lot like the last one we did. So that's 1 over 2 to the first, plus 1 over 2 squared, plus 1 over 2 cubed, plus 1 over 2 to the fourth, plus dot, 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 meaning we keep on adding forever. Okay, so let's look at the partial sums. First partial sum is the first term. The second partial sum, 1/2 plus 1/4, which is 3/4. The third partial sum is 1/2 plus 1/4 plus 1/8, which is 7/8. And the fourth partial sum, 1/2 plus 1/4 plus 1/8 plus 1/16 is 15/16. And I'm thinking maybe that's enough for us to see a pattern in our sequence of partial sums. So let's write down that sequence of partial sums. 1/2, comma 3/4, comma 7/8, comma 15/16, comma dot, 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 comma. And so let's see, have you detected a pattern in these first four partial sums so that you could make a formula for S sub n? Let's look at the denominator first. Those denominators are powers of 2. So the first one is 2 to the first, the second one is 2 squared, then 2 cubed, and then 2 to the fourth. So I think it's safe to say that our denominator for S sub n is 2 to the n. And how is the numerator in this sequence of partial sums related to its denominator? Well, in every case, it's 1 less than the denominator, so we could write that algebraically as the denominator 2 to the nth minus 1. Okay? And so if we wanted to find out if this sequence of partial sums converges, we do the limit as n approaches infinity of our S sub n formula that we just came up with. Oh, by the way, I didn't finish right up here. This is 2 to the n minus 1, we now know, over 2 to the nth, comma, dot, 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 going on forever. So again, that becomes infinity over infinity. So the limit as n approaches infinity, what am I saying? I'm writing the same thing again. As x approaches infinity, of 2 to the x minus 1 over 2 to the x. It's infinity over infinity, so we can use L'Hopital's rule. And the derivative of 2 to the x minus 1 is 2 to the x times the natural log of 2. And the derivative of 2 to the x is 2 to the x times natural log of 2. Algebraically, that simplifies to be 1. And the limit of the constant is that constant. So that implies that this series has a sum of 1. So the series, let me just conclude with a statement. The series from n equals 1 to infinity of the formula 1 over 2 to the nth converges to 1. Which means if you add up those infinite number of fractions that have that pattern, then you'll get an answer of exactly 1. All right, so let's look at the next example, part B. This series, this time, is again going to start with 1. And the formula for producing the terms of this series is 1 over n minus 1 over n plus 1. So if we start expanding, 1 over 1 is 1, minus 1 over n plus 1 will be 1/2, plus, now we're putting in 2, 1 over 2, minus 1 over n plus 1, which will be 3 in the denominator. Next one, now we're putting in 3, 1 over 3, minus 1 over 3 plus 1 is 4. Right, plus dot, dot, dot. And when we put in n for the nth term of this series, it's of course 1 over n minus 1 over n plus 1 plus dot, dot, dot. Okay, so let's see if we can find S sub n, meaning we're going to add up the terms of this series only to a certain point. We're going to add until we put in n into the formula itself and stop. So the first part of this, of course, looks exactly the same as what I wrote above. The big difference here is that when I get to that nth term, that's the last one, and I'm going to stop. Dot, and that's 1 over n minus 1 over n plus 1. Stop. All right, so let's see what we can do with this. Well, you may have, when I was writing this down, you may have noticed, and I kind of hope you did, that the second half of our first term and the front half of our second term add up to be 0. And the back half of the second one added to the first half of the third one adds up to be 0. So if this pattern is continuing, which it should, the back half of this one will add with the first term of the next one, and that'll keep happening over and over and over again until we get almost to the end. The last part of the penultimate term and the first part of the end term will add to 0. And this addition of a whole bunch of zeros makes this collapse quite nicely to be, of course, the initial one, the first half of the first term, did not go away. Then we have a bunch of zeros added. And then the other thing that didn't go away is the last part of the last term, so minus 1 over n plus 1. When this happens, this type of series is called a telescoping series. And anytime I give you a named series, that means it's important and you need to memorize stuff about it and how to deal with it. And we'll be talking about this more later, but I did want to mention, as soon as I say, oh, this is a certain type of series, that's important. Kind of keep that in mind. And what happens, if you think about a telescope, that looks sort of like this, with smaller and smaller pieces, that can collapse if we push on the small end, and it collapses down to something that's about this big. And so the collapsing of the telescope is like the collapsing of this series, and all we're left with is the first half of the first term and the latter half of the second term, of the ending term. So since we found S sub n, we didn't even find the sequence of partial sums this time, which sometimes happens, so you can kind of say, ooh, this one's cool because I didn't have to do as much work. And that's true. So if we want to take the limit of S sub n to see if the sequence of partial sums converges, which would in turn tell us what the series does, we'll take the limit as n approaches infinity of 1 minus 1 over n plus 1. And of course the limit of the constant 1 is 1. The limit of any constant divided by a power of n is going to go to 0. And so that means that the sum of this series is 1. So the sum of the series is 1, which means, of course, that this series from n equals 1 to infinity of 1 over n minus 1 over n plus 1 converges, and it converges to 1. In the directions I give for some of these problems, the question will say, does this series converge or diverge? If it converges, can you find out what it converges to? And so that's why I'm saying it converges to blank, because that's going to be part of the directions. And of course that's the sum of that infinite series. All right, so let's look at part C, or example C. Let's look at this series. N equals 1 to infinity. 1. So we put 1 in for n, there is no n. So we get back the constant 1 plus, now put 2 in for n, there is no n. So we get 2. Oh, what am I saying? So we get 1 again, the constant. We get 1 back. We put in 3. There is no n, so we just get the constant, etc., etc., etc. So the first partial sum is 1. The second partial sum, 1 plus 1 is 2. Third partial sum is 3. The fourth partial sum is 4. So the sequence of partial sums is 1, 2, 3, 4, etc. The nth term is going to be, oh, what am I writing? I'm writing the wrong thing. It's going to be, well, let me write this down below it because that does tend to help. What do I do to n to get that output? And I'm hoping you're going, oh, duh, it's n. You're right. And so, what is the limit as n approaches infinity of n? Well, that's infinity. And when we get a limit that's infinity for the general term for a sequence, when the answer is infinity or negative infinity, our implication is that the sequence diverges. And so this says that the sequence diverges, sequence of partial sums diverges. And then our final conclusion is, well, if the sequence diverges, therefore this series, n equals 1 to infinity of 1, diverges. And of course there's no sum, so we don't have to say and it diverges to, because if it diverged to something, then it would be a convergent thing. And so, yeah, it just diverges. That's all you say there. Okay, so In the next page you see kind of a general, well, it talks about our telescoping series and then generalizes that it's always going to be a difference of two things, and the latter part of the first thing and the first part of the second thing are opposites, so they add up to be 0, and that happens consistently throughout. And so that's what we call a telescoping series. And so what you'll get, like we did up above, is that S sub n is the first half of the first term and minus the latter part of the ending term, the n plus 1 term. Since b sub 1 is going to be a number, all we have to do is test to see if b sub n, the formula, which is the same as b sub n plus 1 in this case, it's just the next term, if that b sub n, well, let me write that down, because I don't want you to be wondering too much about what I mean. So if I wanted to take the limit as n approaches infinity for a telescoping series, I'll be taking the limit as n approaches infinity of S sub n, and we've just established that for telescoping series, that's always b sub 1 minus b sub n plus 1. And the limit of the constant is the constant, so we'll get back this, minus the limit as n approaches infinity of b sub n plus 1, which is just another generic term, just like b sub n is. So if that limit, more generally and probably easier to think of, if the limit as n approaches infinity of b sub n, the latter part of that formula, is a convergent, I'm sorry, if the limit exists and is a real number, then the series converges. And it converges to b sub 1 minus whatever that limit is you got. Okay, so I think this is going to be a good place to stop because, yeah, I'm out of room at the bottom here, so we'll continue in the next video.